Alrighty, so I thought we'd start with something I said at the beginning of last class, which is that in macroscopic systems, decoherence is very fast, very efficient, and I gave the kind of relationship of that observation to Schrödinger's cat, but you can actually formalize that a little bit more, so I thought we'd do that just to start before we talk about T1, and T2, and T2 star. Okay, so Schrödinger's cat, right? It's facing this life or death situation. There's this automatic device that's going to break a vial of poison and kill the cat if an excited atomic state is observed to decay. So we have the state in the excited state, and if it decays, the vial will crack and the cat will die. So Schrödinger asked what happens when the atom is in a superposition state. So instead of being just in the excited state, what if it's in a superposition state? Is the cat alive or is the cat dead? And this kind of leads to the thought experiment, like why don't these superpositions apparently exist in everyday life? And so you can think about the joint system of the cat and the atom as being in the initial state alive, 1. And if you suppose that after one half-life of the atom, the state for the atom moves from definitely 1 to in a superposition state. So we're in 0 plus 1 over square root of 2. So this represents, a simplification of the system, but this is how we'll estimate it. And so this gives us a state for the cat atom system of psi equals dead 0 plus alive 1 divided by square root of 2. So the cat state has become entangled with that of the atom, and this is why people say that this seems to be that the cat is simultaneously dead and alive. But if we actually consider the density matrix for the system, then we can kind of understand what's going on here. So the density matrix looks like the outer product of the state I just wrote down. So it's 1/2 of alive 1 times alive 1 plus dead 0 times dead 0 plus alive 1 times dead 0 plus dead 0 times alive 1. And so in practice, it's impossible to perfectly isolate the cat and the atom in their box, and information about this superposition state will leak into the external world. So for example, heat from the cat's body would permeate the walls and give somebody outside an indication of whether the cat is alive or not. And those effects, those that leaking of information to the environment can be modeled as phase damping. So you're exponentially damping out the final 2 off-diagonal terms in your density matrix. So to a first approximation, you can model the cat atom system as a simple harmonic oscillator. And an important result about the decoherence of that kind of a system is that the coherence between states of high energy difference decay faster than between states with a lower energy difference. So our density matrix quickly becomes transformed into basically a nearly diagonal state that represents an ensemble of cat atom states that correspond to either dead or alive and not a superposition of the 2 states. So decoherence is the reason the cat is not in a superposition state. Okay, so let's formalize our conversation of coherence a little bit more by introducing T1, T2, and T2 star. So these are the sort of 3 important measurements that we think about when we're thinking about how long our qubits have to live, have to do useful quantum computations. So these are single qubit measurements, T1, T2, and T2 star. And so we can use the block sphere to kind of discuss them. So let's talk about T1 first. So T1 goes by lots of different names. You can think about it as a relaxation time, thermal relaxation, longitudinal coherence time, amplitude damping. But essentially what it is, it's related to the loss of the quantum state of energy as the quantum state decays from its excited state back to its ground state. And the energy is transmitted to or leaked into the environment and lost from the qubit. And we measure T1 typically in seconds or some fractions of seconds. And for the computation of T1, what we do is we move the qubit via an X gate from 0 to 1. And then the decay towards the lower energy state 0 is exponential. And it follows the probability P1 equals e to the minus t over T1 for some constant T1. And informally, the larger the value of T1, the longer the qubit is staying closer to its excited state. Okay, so how do we do this measurement? So it's a pretty straightforward process. We initialize our counter. We're going to just be counting the number of times we see this decay happen. So we initialize our counter to 0. We initialize our time to 0. We initialize the number of runs per time increment to some integer, and then we choose a little interval in a little interval. And then we're going to set the increment between measurements to some delta t, and we're going to add delta t to t. And we're going to initialize our qubit to 0. We're going to apply the X gate, and we're going to wait. And then we're going to measure. And if we see the excited state, we're going to add 1 to our counter, and then we're going to go back to repeat this n minus 1 times. And then after n minus 1 times, we're going to compute the percentage of times that we've seen the 1 state. We save it, and we plot it, and we can keep doing this measurement until the percentage is less than this little interval that we chose. So what it looks like after we do that kind of series of measurements, so we're just taking our qubit from our ground state, applying X, that puts it in the excited state, and then we're just watching, counting the number of times we see 1 or 0. So the decay of the quantum states for 2 qubits, Q1 and Q2, are shown here in this graph. And the T1 time is the value of T when PT is equal to 1 over E. So you can see the 2 T1 times for our 2 qubits shown here. And so in this example, Q2 has a larger T1 than Q1. So given that we know that the probability of getting R1 is equal to this exponential function, we can write down the probability of 0 as just 1 minus that. And so if you wait 4 times T1 seconds, then the probability of you getting 0 is e to the minus 4, which is about 0.98. So about 98% probability that you're going to be in the ground state if you waited 4 times the T1 time. And if you wait 10 times T1, the probability is e to the minus 10, and that's like 0.99995. So with almost 100% probability, you'll get 0. You'll be relaxed. So this idea of the probability of being back to the ground state as a function of the number of multiples of T1 is the basis for the classic inversion recovery experiment in NMR. So if any of you have done some organic chemistry and wanted to quantify yield or something using an NMR spectroscopy experiment, then you might have done this experiment. And so this T1 relaxation time, when we think about it from the perspective of our nuclear spins in NMR, it's the longitudinal relaxation or the spin lattice relaxation in the z direction. And it's the process by which the net magnetization returns to equilibrium along the z-axis in our little solution of spins. And so we describe that mathematically for this NMR experiment as with this equation. So the magnetization along z is equal to the initial magnetization times 1 minus 2 to the e to the minus t divided by t1. And the method that's most commonly used to measure T1 is this inversion recovery experiment shown on the left. And so what you do is you apply the 180-degree pulse. That's our x gate, right? We wait some time t, and then we apply 90-degree pulse. So in NMR, all of the measurement is done in the xy plane. That's why you need the 90-degree pulse at the end. You can't measure your signal if you're not in the xy plane. And so the graph on the right is showing the relative intensity of the recovery magnetization versus time. And the sample here is a 40% water in D2O mixture. And so then you can ask yourself, so in NMR, why is it important to know the value of T1 for the species that you want to study? And it's important comes from the fact that it affects the relative integration between protons in your experiment. Because each nucleus, which is an individual spin, in a molecule has a different T1 time. So if I think of this molecule, feroic acid, and I'm taking a proton NMR spectrum, I have these 3 protons here, H1, H2, and H3, and they should each integrate for 1 in my NMR spectrum. If I set my delay time in my NMR spectrum to 0, and I just collect it, and then I integrate the 3 peaks corresponding to those 3 protons, it's not 1 to 1 to 1. It's like 0.87 to 0.98 to 1. And that's because we haven't allowed enough time for all of the proton spins to relax back to the same extent. So what we do is, well, what you should do is you should measure the T1 time of your molecule and then set your delay time to be 5 times T1. And so in this second experiment, they set their delay time to 30 seconds. So that's probably more than 5 times T1. And so now you see that the integrals for the 3 peaks are all equal to 1. Cool. All right, so what about T2 and T2 star? So if T1 was concerning itself with going from the South Pole to the North Pole, T2 is adding in this extra element of what's happening on the equator of the block sphere. You can basically think about it as how long we have to run operations before our quantum information is lost. All right. So T2 and the related metric T2 star, we'll talk about them separately, go by lots of names, just like T1, depending on who you are and what your qubit system is. Dephasing time, elastic scattering time, phase coherence time, phase damping time, and transverse coherence time. And so in a perfect world, if we used this circuit, so we have our qubit, it's in the 0 state, We apply a Hadamard gate, so now we're on the equator. We wait some time, so our identity gate there is just our time delay. And then we apply a Hadamard gate again. If we had a logical qubit, we should get back 0, right? We took our 0 state, we put it on the equator, we waited, we reapplied Hadamard gate, we should be back to where we started. So that's in a perfect logical qubit. So this is just a identity gate, so kind of a time delay. The H's here are our Hadamard gates. So if we move to the equator and then go back to 0, we should note that neither 0 nor 1 has a phase component. And so if we want to study how the phase of our qubit is evolving with time, we need to do the experiment somewhere where there's phase information. So the equator is a really natural choice, which is why you do this, this sequence. Okay, so a physical qubit, however, isn't perfect. And instead, once we move to the equator, so we go from 0 to plus, we're on the equator, we begin drifting a little around the xy plane. And so in this example that you're seeing on the block sphere, once we get to plus, we move counterclockwise by some angle phi. So that means the qubit state isn't stable. And we're also expecting that during this time, the state's going to be moving to a lower energy. But in this experiment, we're just focusing on what's happening with the phase. So the same goes for when we're doing our T1 measurement. There might be phase drift, but we're just focused on the longitudinal decoherence. Okay, so we can express this circuit here that we've just kind of laid out. So take 0, Hadamard, identity, Hadamard, measure, in matrix form. And so it's written out here. So we have our Hadamard gates, square root of 2 over 2, square root of 2 over 2, square root of 2 over 2, minus square root of 2 over 2. We have, so matrix form. So we can kind of go through and rewrite the matrix form as we have here. And this allows us to see that when phi is equal to 0, we get 0, like we expect. And when it equals pi, then our rotation here is a rotation by pi. That's the same thing as if we did a z-gate, and the result is 1. Okay? So phi is 0, we get 0. Phi is pi, we get 1. And when phi is somewhere in between 0 and pi, then the amplitude of 0 is going to be equal to 1/2 times 1 plus e to the I phi, which is just 1/2 times 1 plus cosine phi plus I sine phi. So the probability of getting 0 is the square of that. So 1/4 times sine phi squared plus cosine phi squared plus, 2 cosine phi plus 1, which is just equal to 1 plus cosine phi over 2. So the phase change, if the phase change continued at a constant rate over time, you would expect the graph to look like this. If I was plotting the probability as a function of time for measuring 0, this is what it would look like based on what we just wrote down. But instead, there's a decay toward a probability of 0.5. You get the same short-term periodic behavior, but it's short-term because eventually the quantum state decays fully to 0. And the final Hadamard gate will place the state on the equator. And at that point, the probability of getting 0 is exactly a half. So the quantum state eventually fully decays to 0. And the final H will place the state on the equator. And so that means the probability of getting 0 is exactly a half, which is why we're decaying towards a half. All right, so this measurement that we just described is what you do to measure T2 star. And the circuit that we described, so this circuit, the Hadamard gate, identity, Hadamard gate, measure, is called the Ramsey circuit, or the Ramsey experiment. So we're considering the wait time between the Hadamard gates here, and during this time, some rotation phi around the z-axis occurs. And everything we just showed in these plots here sort of assumes only one kind of noise or decoherence, the phase drift. And even that was constant, which is not a guarantee in our real qubit systems. There's going to be other noise and other irregularities that are going to affect the coherence, including the longitudinal coherence. So for small enough intervals of time, T2 star is basically the largest time where the probability at that time is less than or equal to 1 over e. So T2 star is the largest time where P of t is less than or equal to 1 over e. So that's right here. All right, so what about T2? So T2 is a very related concept that is measured via an experiment called the Hahn echo. Here we go. All right, so the experiment says, okay, I'm going to start with my state in the ground state. I'm going to apply the Hadamard gate. That brings me to the equator. I'm going to wait. Then I'm going to apply an X gate. That's going to bring me back. Then I'm going to wait. And then I'm going to apply Hadamard gate again. So you can see the experiment in the GIF here in the top right. So Hadamard gate, that's a 90-degree pulse. X gate, that's a 180-degree pulse. Hadamard gate brings me back. Okay, so the difference from T2 star is that instead of waiting the full time before the final Hadamard gate, we wait half as long, and then we do an X gate, 180-degree pulse. Then we wait the remaining time, and we conclude with the Hadamard gate. And so by doing this, we're canceling some of the phase drift, but we're keeping the effects of other noise. And so this technique is called a refocusing technique. It is essentially giving us very similar information, but allowing us to keep the effects of other noise and just kind of cancel out some of that phase drift. So in general, there's this equality that you'll see written numerous places. So T2 star is less than or equal to T2 is less than or equal to 2 times T1. So in the absence of pure dephasing, T2 is equal to 2T1, and I'll show you that from the perspective of MRI, an MRI explanation in just a minute. And the process of relaxation alone will upper bound the phase coherence of the qubit. Okay, so those are our three measurements, T1, T2 star, and the related T2. All right, so let's look at an example where these measurements are done all the time to give us information about a system. So in magnetic resonance imaging, contrast in the image is obtained through three mechanisms: T1 recovery, T2 decay, and proton density measurements. And the image contrast depends on how much we allow each process to happen. So in the image that I'm showing here, I'm showing an example of T1 contrast and weighting. And the T1 time of a tissue is the time it takes for the excited spins to recover and be available for the next excitation. So it's exactly the NMR experiment I described earlier. And so in this example, you're looking at contrast between fat and cerebrospinal fluid, so that's CSF, in the human body. And the frequency of hydrogen atoms in cerebral spinal fluid of the nuclear relaxation, or the frequency of the hydrogen nuclei, is higher than that of the hydrogen in fat. So hydrogen atoms in the fat recover more rapidly along the longitudinal axis than cerebral spinal fluid. So hydrogen fat recover more rapidly. So as the T1 time of fat is shorter than the cerebrospinal fluid, the fat spins realign with the applied magnetic field faster than that of the cerebrospinal fluid. And so the longitudinal magnetization of fat is larger than cerebrospinal fluid. Okay, so when we do this measurement in an MRI experiment, we are plotting the signal intensity against repetition time, which is this TR here. So after a certain repetition time, the next radio frequency excitation pulse is applied, and this will flip the longitudinal magnetization of fat and the cerebrospinal fluid towards the transverse plane. And because there was more longitudinal magnetization in the fat before the radio frequency pulse, the net magnetization vector of the fat spins can be flipped into the XY plane more easily than can the spins in the cerebrospinal fluid. So this means that the contribution from cerebrospinal fluid to the overall signal will be too small in comparison to the fat. And so the fat has a high signal and appears really bright in the T1 contrast image, and the low signal cerebrospinal fluid appears dark. And that's why it's called a T1 weighted image. So right, this TR, the relaxation time, is the length of the relaxation period between the two excitation pulses. And it's therefore kind of the critical factor when we're thinking about this T1 contrast. So the repetition time controls how far each spin can recover before it's excited by the next radio frequency pulse. And for this T1 weighting, the repetition time has to be short enough so that neither the fat nor the cerebrospinal fluid has sufficient time to fully recover to beat the applied magnetic field. So you can see that in this graph here. If the repetition time is too long, then both the fat and the cerebrospinal fluid will fully recover to the longitudinal magnetization, and in that case, the difference in contrast won't be seen in the image. So you want to be operating sort of in this short repetition time regime where there's a difference between the two. So you don't want them to fully relax. So in the NMR experiment we were talking about, we want them to fully relax so that they can be weighted equally and we can accurately integrate those signals. Here, we're kind of intercepting and we're measuring before they've fully relaxed so that we get that contrast. All right, so you can do another type of experiment in the magnetic resonance field, and it's related to measuring T2. So in this same example of fat versus cerebrospinal fluid, the T2 time determines how quickly the magnetic resonance signal fades after excitation. So the T2 decay occurs as a result of energy transfer between spins in your sample, and the energy exchange of hydrogen atoms in fat is more efficient than in water. So as a result, hydrogen in the fat loses its transverse magnetization more rapidly than the cerebrospinal fluid. So the magnitude of the transverse magnetization in cerebrospinal fluid is large, and so it appears very bright as compared to fat in the T2 contrast image. So the utility in doing both measurements is you flipping the contrast. So in the T2 measurement, the cerebrospinal fluid is bright and the fat is dark, and in the T1 contrast, the cerebrospinal fluid is dark and the fat is bright. All right, so in this T2 measurement, your kind of key time interval is called the echo time, related to the Hahn echo pulse sequence that we just talked about. So it's the interval between application of the excitation pulse and collection of the magnetic resonance signal. And if a short echo time is used, so let's say here 25 milliseconds, the signal differences between the tissues are small because T2 relaxation has only just started, and there has only been a little bit of signal decay at the time of the echo collection. And so the resulting image that you would get wouldn't really have any contrast. But in the case of this T2 measurement, if we wait a long time, if the echo time is long, let's say here 100 milliseconds, the tissues with a short T2 time have lost most of their signal and appear dark on the image, while tissues with a longer T2 produce a stronger signal and appear bright because they haven't fully decayed yet. I mean, you can ask, why would you do both of them when you're measuring the properties of a qubit, right? I mean, it gives you kind of complementary information in terms of like diagnosing an illness. Just the visual interpretation of the data, can look a little bit different and can give you, maybe you can analyze the bright regions more precisely than you could when they were dark. So like here you can analyze, the form of the cerebrospinal fluid or the distribution of the cerebrospinal fluid better than when it was dark. So it just gives you kind of more information. All right, so I said that we'd get back to this question of T2 less than or equal to 2T1. So when you are reading papers about making materials and platforms for qubit technologies, you often see people measure T2 and measure T1, and they're like, oh, look, T2 is close to 2T1. That's great. So I think the question comes, why this equality? And so we can kind of think about this from the lens of magnetic resonance imaging that we kind of just described. And so in this MRI experiment, the T1 and T2 times the constants, they're describing how fast nuclear magnetization returns to an equilibrium value. And we're going to call that equilibrium value M0 so returning to equilibrium after excitation by your radio frequency pulse. So T1 is describing the exponential recovery of the longitudinal magnetization. And T2, so the longitudinal magnetization is the magnetization parallel to the external magnetic field. And T2 is looking at the exponential decay of the transverse magnetization. The decay, not recovery. And that's the precession in the plane orthogonal to the magnetic field. Okay, so in this top figure, we're seeing kind of a typical scenario where T2 values of tissue are considerably slower than T1 values. So the transverse magnetization decays quicker than the longitudinal relaxation needs to recover. So for most tissues in vivo, T1 varies between about 300 milliseconds and 3 seconds, while T2 varies between about 10 milliseconds and 200 milliseconds. Okay, so we want to know, is there a good physical reason behind this T2 to T1 relationship? So to analyze this, what we can do is plot the longitudinal and transverse relaxation together in a diagram showing the transverse magnetization on the horizontal axis and the longitudinal magnetization on the vertical axis. So that's what we're doing. Transverse X, longitudinal Y. And the relationship here, the total magnetization squared, is equal to the sum of the squares of the longitudinal and transverse magnetizations. And that line that defines the total magnetization here is this black curve. Okay? So this is kind of the boundary. All right, so what these two diagrams are showing are the evolution of the magnetization after a 90-degree radio frequency pulse. And this left-hand graph that I've written on so far is showing 3 cases where T2 is equal to T1 divided by 2. That's the dark blue curve, where T2 equals to T1. That's the green curve. And where T2 equals 2 times T1. That's the kind of cyan curve. And all 3 of these curves show sort of a normal behavior. They lie within this shaded region below the kind of black-red now border where the longitudinal magnetization squared plus the transverse magnetization squared equals the total magnetization squared. So this means that the magnitude of the total magnetization vector is always smaller than M0. In the right-hand side, it's showing what's happening if T2 becomes greater than 2T1. So the specific case that's plotted in red is T2 equals 3T1. So now the magnitude of the total magnetization vector increases above the physical limit of M0. So the red line is crossing that border of physically normal behavior. And so you can show mathematically that the maximum T2 value in which the curves stay below the kind of border line is exactly T2 equals 2T1. So that's kind of why you normally see this equality, and so you might ask yourself, is this always true? Could you have any system where T2 is greater than T1? And of course, yeah, there's going to be exceptions. They're very rare situations when the spin relaxation is caused by fluctuating microscopic fields that are predominantly transverse rather than longitudinal. It could happen. And one mechanism that gives rise to fields of that form involves the antisymmetric component of the chemical shift tensor. Molecular systems where that is dominant is extremely, extremely rare. I can send you guys maybe a paper that looks at a system where that's the case. But in general, most systems are going to live below this kind of normal longitudinal squared plus transverse squared equals total squared. Cool. There's more rigorous mathematical ways, like I said, to demonstrate this, but I think for the sake of what we just went through, this is kind of a nice way to grasp it.